Hello and welcome to SciJoy. This video comes to you in two parts. One, I want to talk about a grad school project I did where I got to break a bunch of stuff. And two, I want to talk about a machine learning challenge where you learn about machine learning and what it's about for 100 days. And the only machine learning I've ever done was with this grad school project. But first, let's start back in undergrad. So I was a part of a rocketry club and we wanted to send a rocket to the edge of space, which is about 62 miles up, I think. But we launched our rocket and only got to about 40. So the next generation decided they were going to try and actually hit that milestone, and to do that they were going to make a lighter motor casing. And they were going to use aluminum like we did, but they're going to make it thinner, and then they're going to wrap it in composites. So they had carbon fiber, and it's woven together into fabric, and then you have different layers of that, and you put them on top of each other into the shape you want. It's pretty flexible at that point. But then you add resin, which is kind of like a glue, and it cures or hardens, and it takes this shape. And carbon fiber is a lot lighter, and it's also very strong. So they hoped that reduced weight was going to be able to get them to the proper altitude. And I said I would help them test to make sure that it was still as strong as they needed to have it be. So when it was pressurized, it wasn't going to explode. It was going to have all the pressure come out one end and shoot the rocket forward. So that's what I was doing with grad school. I was listening to how the composite was failing as we pressurized it. We were doing something called a hydrostatic test, where you put water in it and you increase the pressure and see at what pressure it's going to just catastrophically break. And I was using something called Acoustic Emissions Sensors, which is just a fancy way of saying I was just listening to the composites and seeing how they failed. So like when there's an earthquake, it releases energy and it radiates out in all directions. There's waves, and you use seismometers to see how the waves are lifting the ground up. You do the same exact thing with acoustic emission sensors. But the only difference is these are much tinier because these breaks are so much smaller. So we have a different parts of this piezoelectric sensor. So you have the couplant, which is how you attach it, and then you have the actual internal part, which is the piezoelectric. And if you remember from our time series, we had pieces of quartz, and we would add an electrical signal to the quartz and it would oscillate at a certain frequency. I think it's like 32,000 times a second. And this is how we kept time, by these oscillations. But you can do the reverse. So with the quartz, we added an electrical signal and we produced a mechanical vibration. But if you're using the piezo to detect mechanical vibrations, then you can create an electrical signal. And this signal is very, very small. So we have to have an amplifier to increase the signal, and we have a filter to get rid of some of the noise. And those are both inside the casing of the actual sensor, because the noise from the wires could interfere with it, so you want it really, really close. And when the signal comes out, you compare it to something called a reference voltage or a threshold voltage. So anything below this voltage is probably just some kind of noise. So we want a nice clean signal. And this signal is going to tell us a lot of things about how this composite is breaking. So there are three failure mechanisms that we're looking at. The first failures that usually happen when we're pressurizing this are in the matrix. So that's where the resin is. That's the weakest part. And that's also sometimes where manufacturing defects are. So those are usually the things to break first. And it's the weakest, so it doesn't have a lot of energy with it. And when you have these little waves go across, they don't last for very long. The second kind is delamination. So that's when the different layers of the fabric are actually shifting and coming apart from each other, and that's over a much larger surface area. That takes longer time to happen, and it's pretty energetic because it's such a big surface area that we're working with. And the third part is fiber breaks. So the carbon fiber fibers themselves are very strong. That takes most of the strength when you're pressurizing it. That's what's taking that pressure. So those happen towards the end, and when those break, you know that things are coming towards failure, when a lot of them are breaking. And they're very quick events, but they have medium to high amounts of energy when they fail. So we can tell what kind of failures are happening by just looking at the signal. So we have our voltage is coming in, and we have the signal, and anything that's above the threshold voltage is what we're seeing. And we have something called a peak amplitude. So the voltage itself is also sometimes called an amplitude, and the peak amplitude is the highest voltage that we're seeing. And since we have two different peak amplitudes on here because we have two different events. So an event is the first time the signal goes across the threshold. to the last time it goes across the threshold. And then we have another event here because it crossed the threshold and then it went back under again. So these events happen in different durations. And like we said, if you're having a delamination event, you're going to have a longer duration. And if you're having a matrix crack or a fiber break, it's going to be a shorter duration. So that's how we can tell which one's happening. And then this red area that we have colored in here is called the energy. And more energetic event would be delamination, and less energy would be a matrix crack, and a medium one would be the fiber because it doesn't happen for too long, but it does have more energy than a matrix crack does. And counts are every time that the signal goes over top of the threshold. These are a couple of the things that we can look at the signal to tell what kind of failure that we're having. But when we're looking at failure mechanisms, it's really nice in textbooks to see these nice little signals, and they don't have a lot of noise, or you see these histograms where it's like, this kind of failure mechanism is lumped over here statistically, and this one's over here, and this one's over here, and there's only like a little bit of an overlap, but when you're working with real world data, there's lots of overlap. And you also have multiple breaks at the same time, because when the matrix starts breaking, you're putting more load on the fibers, and then they start breaking, and they put more load on everything else, and then it kind of all meshes together, and you just have a catastrophic failure. So when you're trying to parse these all out, it's pretty hard for a human to do, so we try and get machines to help us out with this. So this was the first time that I ever used machine learning, and I didn't even know it was called machine learning. It was called a self-organizing map, and that's what I used to figure out what categories of failures things were going to. So self-organizing maps are a neural network, and they have a categories layer and an input layer for the one we're using. It's just a two-layered neural network. And this first layer over here are the inputs, and these are just the different features we saw in our waveforms. So energy counts, frequency, amplitude. Frequency is counts over duration. So you can see some of them are kind of mixed together and they're not completely independent variables. And it'd be hard for a human to look at all of this and parse out patterns, because maybe we're looking at counts and it's a kind of a low medium count and we're like, oh, is this a fiber break? Is this a matrix crack? I'm not really sure. And then you'd have to go over to the energy graph and be like, oh, well, it has a lot more energy, so it's probably a fiber break, and there are thousands of data points to do this for. So the self-organizing map is going to look at all these different dimensions and it's going to group them accordingly and be like, well, I think this is a pattern of over here, and this is category 1, this is another pattern, this is category 2, and this one over here is maybe category 3. And if you give it more categories, it will lump it into 4 or 5. And I tried 10 categories at first, and then I went down to 5, and then 3 seemed to be the best fit, where you could really distinguish that there are 3 different kinds of failure mechanisms. And how it does this is if you look at a graph, and this is a very simple graph, it kind of skewed it so there are some patterns already, and there aren't a lot of data points. Remember, it's looking at thousands of data points. So these are your categories over here, and this is what I remember from grad school. And part of the reason I want to do this machine learning challenge, is to learn a little bit more about it. But from what I remember is you have these 3 different categories, and they're randomly assigned locations in the beginning. And then it's going to go through each of these data points, and when it's looking, it's thousands of data points with multiple categories. And it's going to shift these different categories according to how close it is to a data point. So if we're looking at this first data point, the square, category 1, is closest, and it's going to shift the most that way. And these are just going to move a teeny tiny bit towards that first data point, because they were farther away, but we're still going to shift everything over. And then we're going to go through each one of these data points more and more, and at the very end, we're going to have shifted these 3 categories, and we're going to have made kind of patterns that we can lump everything together with. So maybe at the end, this is one category of failure, this is another category of failure, and this is the last one. So it's shifted these all around, looked at every single data point, and it's like, yep, these are the 3 categories that we see. And then it's up to the human to go in and be like, okay, this category 1 is, matrix cracks, this one's fiber, this one's delamination, or however it's going to go, the human will decide that portion. So self-organizing maps just look for patterns. That's their main goal. To validate that this actually works, it's a little bit different than other neural networks. Sometimes you'll have ones that are called supervised, and that means that they are trained on data. So you give it some of your data set, and you see what it does, and then you do test data set to see if those results were accurate. So this is unsupervised, so we don't have training and testing data. So what happened instead, some other grad students did simple breaks on composites, and so there wasn't a lot of overlap, and you can kind of tell what mechanism was happening at what time. And they did a Johnson distribution, so it's just a statistical analysis, and they found different patterns in that and compared it to the self-organizing map, and they validated that yes, the self-organizing map was working. So pretty much this neural network, all it does is you give it some inputs, and then it looks for patterns according to how many categories you give it. So now that I had the different failure mechanisms, I could see over time how it was failing and when it was starting to become catastrophic. And we did take it to the complete breakdown of it, and it failed at the attachments points, which is where we expected it to fail. That's the weakest part. But a lot of times you use acoustic emission sensors to figure out how things are failing in real time. So you could put them on bridges and see if there's cracks in the cement or if there's breaks in any of the wires for a suspension bridge. And everything's engineered to hold more weight, so it has factors of safety, so it can hold 2 to 5 times more than it sees in a daily use. So if one little part of it breaks, you go fix it and everything's still fine. And you can fix it before it becomes too much of a problem. And if we were to do real-time monitoring on aircraft, you would do cyclic loading. So when you're going up, you're pressurizing, and when you come down, you depressurize. So you're going through cycles, and you want to know when that fails. So one of my friends did a thesis, and he used 2 kinds of machine learning to be able to do this. So he took pieces of aluminum that had a notch in them, and you would use tension, you would pull on them, and they would release them. You go through cycles, and you would see how many cycles you could go through before they would break. And he used the self-organizing map to figure out what kind of failures we were having, and then he used another thing called a backpropagation neural network, and he trained that. So he said, okay, here's 30 different things that I broke, here's 15 of them, and figure out when they broke. So he trained it to say, this is what you're looking for, these are the different failure mechanisms. When you see these cues, like it figured out, like when you see these cues, you know that the cycle is coming to the max cycles and it's probably going to break. And then you used 15 of the other ones that he didn't train it on, you use that to test it. So you put that in, you know what the answer is because he broke it, and you put that in and he saw, like, did it actually predict when that would fail? And it did it pretty well. And so that's how you can use machine learning. You can use it, 1, to categorize things, or 2, we used it to predict when failures would happen. And this is the only machine learning I've done so far. But there's a machine learning challenge, and I'll put a link to the video that tells you more about the challenge. But every day for about an hour, the challenge is to learn about machine learning and then post somewhere the things that you figured out that day. So that's what I want to do, and I hope that you're going to join me with that. I wanted to learn more than just what I did in grad school. And I'm going to post it in a couple different places. If you want a really in-depth version of what I'm learning every day, I'll have a blog post, and it will be at our website and on Medium. I'm going to do these things at different places so you can get it in the format that you want. So that's going to be the most in-depth with links to resources. I'm starting out with Coursera, Udacity, and some books. And then if you want a bit lighter version, I'm going to try and do a daily video on things like Instagram, TV, and Twitter. On YouTube, I'll do hopefully a weekly or almost weekly wrap-up of what I've learned, and that will be more in-depth. But daily, I'll do short video snippets and a little audio version of our Learnings of a Maker podcast. Links to all this will be down below, but I'm going to try and share what I'm learning with you every day, and I hope that you take on this challenge, you learn something every day, and share it also with us. So this is just a preview of what I've done before. This is all I've done with machine learning, and I look forward to learning way more about it over the next 100 days with you.